In this video, we conclude our concepts discussion of Chapter 8, finishing off with the last of the atomic properties, and then looking a bit at magnetism and ion formation. The next property we're going to look at is electron affinity, termed EA. An atom can have an electron affinity, and that is the energy change that occurs when 1 mole electron is added to 1 mole of gaseous atoms of that element. So if we take A and add an electron to it, we form A minus. The enthalpy for that process is the electron affinity of the atom A. The electron affinity can be negative, and that would be a delta H being negative. That would be an exothermic process. That's a stable anion. Or the electron affinity may be positive, and that occurs when we have an unstable anion. That would be something that would be delta H, which is a positive value, that is endothermic. Now you won't see second electron affinities for atoms. You'll only see the first one because once you have one electron, a second one is so strongly shielded and repelled it can't get on. Another side point is this definition is the one that you will use. This is the inorganic chemistry definition, and it's a very common one, but it's not the only one. There are a number of standard tables produced by the government, by NIST and other labs. And they all typically use the chemical physics definition of electron affinity, which is for the reverse reaction. But we won't worry about that. You are likely not to encounter that because there are very few folks in class who will use gas phase electron affinities in the future. We'll need these, though, when we get to Chapter 9, and we'll use this definition. An atom plus an electron goes to the anion. The energetics for that reaction is the electron affinity of the atom. Atoms with low electron affinities tend to be the metals that form cations. Atoms with high electron affinities are the nonmetals, which tend to form anions. But we'll see that the trends in electron affinity are not as regular as those for atomic size or ionization energy. Here we see the electron affinities of the main group elements, those in the S in the P block. And these are all listed in kilojoules per mole. The general trend here, as listed on the right-hand side, the electron affinity tends to decrease down a group. You can see in group 1, the round group on the left, you can see it decreases continuously down the group. In group 17, that green group on the right-hand side, it tends to decrease, though going from fluorine down to chlorine, it actually increases. So there are cases where the trend is not held. The general tendency to decrease down a group is because we have a lower nuclear attraction. We're going to a higher principal quantum number. The electrons are further away from the nucleus, and they're more easy to remove, and hence they're less energetic when you stick them back on. The electron affinity tends to increase across a period for similar reasons as we saw for ionization energy. We have a fixed core, so the effective nuclear charge is increasing, the electron is held more tightly, and that is a rough trend. Overall, the behavior patterns for ionization energy and electron affinity are as follows. The reactive nonmetals have high ionization energies and highly negative electron affinities. And these reactive nonmetals, they don't include group 18. The noble metals are non-reactive. So the reactive nonmetals would include the halogen, chalcogens, and so forth. These elements attract electrons strongly and tend to form negative ions in ionic compounds, something that we've been repeating over and over throughout this course. The reactive metals tend to have low ionization energies and slightly negative or very low electron affinities, low positive electron affinities. The transition metals have been measured and do have favorable electron affinities, though they're very small. There are ones that have positive electron affinities. So these elements lose electrons easily. They tend to form positive ions in ionic compounds. And this is again what we have seen from the beginning. The noble gases, they're their own group. They have very high ionization energies and positive electron affinities. They don't gain or lose electrons. They're happy the way they are. Overall, the trends in atomic radius, atomic size, ionization energy, and electron affinity are shown in these graphics. The upper two include the noble gases. The electron affinity, of course, does not include noble gases because they do not attach electrons. So in the upper left-hand corner, we have our atomic size, the gray boxes. The largest atom is cesium in the lower left-hand corner. That's kind of the lower southwest. And then in the upper northeast, upper right-hand part of the gray box, those have the highest, the highest ionization energy, but the smallest atomic size. So the smallest atom is helium, and the biggest atom would be cesium. Looking at ionization energy, again, that same trend. The helium is going to have the highest ionization energy. Cesium in the lower left-hand side is going to have the lowest ionization energy. The electron affinity tends to increase such that fluorine is the highest. Fluorine and chlorine are up at the top. And then the lowest tends to be cesium, but there are many exceptions in that trend. Another trend we can look at is what we're going to call metallic behavior. We discussed what the metallic properties were earlier when we were classifying elements. Metals are typically shiny solids with moderate to high melting points. They're shiny because they reflect light, and that has to do with their conductivity. It turns out their electrical conductivity. Melting points are reasonably high. We'll find out that's due to metallic bonding later. Metals are good conductors of both heat and electricity. They're ductile and they're malleable. And that means that they can be flattened or drawn into wires, and they can be easily shaped. And they're somewhat stretchy in that sense. Even though they're tough elements, they're stretchy. Metals tend to lose electrons and form cations. That means they're easily oxidized. Metals are generally strong reducing agents. They give up electrons easily. And we saw that earlier when we looked at oxidation reduction reactions in chapter 4. Metals were good reducing agents. Metals tend to form basic oxides. So metal oxides are bases in water. And all of these properties are associated with the looseness of the valence electron. So the looseness by this, the ease of ionization or the ease of removal or the ease with which it can be moved around. And so the looser or lower ionization energy elements tend to be more metallic. And in fact, we see this. So we can look at our periodic table. The most metallic elements are the lower alkali metals. They tend to be the most stretchy elements. And so this is our general trend. Now, there are specific trends in, for example, conductivity and hardness and other things that can fluctuate. So this is a general trend. Now, it is true that the metals on the left-hand side are the most basic, and the metals that are more towards the right are the least basic. But like electron affinity, there are fluctuations in the behavior across the periodic table. This is a general trend. So let's look at one period and then one group. So let's look at period 3. Period 3 takes us from sodium to magnesium to aluminum to silicon to phosphorus to sulfur and then to chlorine. The metallic behavior decreases across this period. Sodium has the most basic oxide. It's the most easily smashed and manipulated metal. Magnesium, of course, though it's an insoluble oxide, it is a basic oxide. Aluminum is an amphoteric oxide. Silicon, then phosphorus is a weak acid as an oxide. Sulfur is a strong acid as an oxide. And then the chlorine oxide forms the strongest acid of all, and that's perchloric acid. Now, going down a group, so if we go, we have group 15 here, nitrogen, then phosphorus, then AS, that's arsenic, then SB, which is antimony, and then finally BI, which is bismuth. We see that the metallic behavior increases, so that the oxide of nitrogen forms nitric acid. That's the strongest acid. Then phosphoric is a weak acid. Arsenic acid is a weaker acid. And then antimony and bismuth form basic oxides. And of course, nitrogen is a gas, whereas bismuth is a shiny metal. Here are the highest and lowest oxidation numbers of the main group elements. And we know group 1 and group 2, we know +1 and +2 for those guys. That trend is very solid, and we've seen that throughout. In group 17 on the right-hand side, the yellow group, we got fluorine, chlorine, bromine, iodine, and acetine. Fluorine's always -1, but the other elements can vary from -1 to +7. And then the next group over, chalcogens, oxygen, sulfur, selenium, and so forth, they can vary from +6 to -2, excepting oxygen. Nitrogen has the most oxidation states of any element, and it can vary from +5 to -3. The carbon group can vary from +4, like carbon and carbon dioxide, to -4, like carbon and methane. And boron can be +3 in that group. We've talked about the acid-base behaviors of oxides. The main group metals form ionic oxides or basic oxides. So the main group metals would be like bismuth or lead or tin. And they are metals, and just like the other transition metals, their oxides are basic. The main group nonmetals form covalent oxides, which are acidic. So nitrogen oxide, N2O5, reacts with water to form nitric acid. Cl2O7, dichlorine heptoxide, dissolves in water to form perchloric acid. Sulfur trioxide, SO3, it's a nonmetal, it's a covalent oxide. It dissolves in water to form sulfuric acid. In between the metal oxides and the main group nonmetal oxides are a few metalloids and a couple of metallic elements that form amphoteric oxides. We mentioned this earlier. These can be acid or base in water. And aluminum, though it is a metal, it's right next to silicon in the periodic table, and silicon is a metalloid, and aluminum is close to silicon, and so it has some metalloid behavior. It is also an amphoteric oxide. So Al2O3, aluminum oxide, can react with hydrochloric acid, or aluminum oxide can react with sodium hydroxide. So when aluminum hydroxide is reacting with hydrochloric acid, aluminum oxide is acting as a base. When aluminum oxide is reacting with sodium hydroxide, aluminum oxide is acting as an acid. Here are the acid-base trends. We've discussed these already, but the blue boxes are the basic metal, they're the metal oxides, which are bases or alkaline materials. The red boxes are the nonmetal oxides, which are acids. And the more red it is, the more strong acid it is. The pinkish ones are weak acids. And the purple one there, aluminum, is both acid and base. And then the blue ones, the more blue is the stronger the base. Strongest base is sodium oxide, Na2O. Next, we're going to look at ions, and this is going to lead us into some interesting behavior. We're going to end up talking about magnetism through all of this. So elements at either end of the period gain or lose electrons to attain a filled outer level. We've recognized this before. The resulting ion has a noble gas electron configuration and is said to be isoelectronic with that noble gas. Isoelectronic simply means that it has the same number of electrons, the same electron configuration. Sodium, as an example, has its shown electron configuration, and the red 3s1 is the valence electron configuration, and that's the electron that comes off, leaving sodium with a plus charge on it, and that's isoelectronic with neon. Below there is bromine, and that's a halogen. That's in group 17. With its electron configuration, a 4p5 is its outer electron configuration, and so we have an electron added to that to make it a 4p6, and that's isoelectronic with krypton. And this is very similar to a slide that we saw earlier this semester, showing our periodic table and how elements on either side of the main, in the main group or in the P block or the S block, will tend to gain or lose electrons to be like the nearest noble gas. So, the electron configurations for monatomic ions. A pseudo-noble gas configuration is attained when a metal atom empties its highest energy level. So let's take as an example tin, that's Sn. The element tin has the electron configuration krypton 5s2, 5p2. In this case, the outer electrons are those with the highest principal quantum number, n, so that would be the 5s2 and 5p2. In this case, when tin does this, the ion attains the stability of an empty ns and empty np sublevel and a filled n-1d sublevel. So it's a pseudo-noble gas. So it has a krypton core plus a filled 4d10 when tin forms its +4 oxidation state. So the tin 4 plus has lost 4 electrons. It will lose the 5p2s and then the 5s2s. So even though the 4d10 filled after the 5s2, when emptying, the 5s2 comes out before the 4d10. A metal may lose only the np electrons to attain an inert pair configuration. So this is not exactly a noble gas, and it's not even a pseudo-noble gas, but we do have the 5s's filled. So tin tends to lose 2 or 4 electrons. We'll do some examples with this in our next video. And what we see here in this graph is an interesting effect. What we've got on the graph is energy on the y-axis and atomic number on the x-axis. The energy is the energy of the various electronic states in the system. So the blue line, the one that slowly decreases and kind of continuously across the graph, is for the 4s sublevel. The green is for the 3d. So you can see once we enter the transition series, The 4s sublevel is more stable than the 3d due to penetration, which we knew that from what we learned earlier. The 4s has a lower angular momentum, so it penetrates more closely to the nucleus. It feels the higher effective nuclear charge. But as we go on, after we cross over, at scandium, the 3d becomes more stable than the 4s. So to form an ion, the 4s electrons are lost first. So on the bottom is our basic set of rules that we need to remember, and these are the rules listed at the bottom are how you need to think about this. In ion formation, electron removal often differs from electron filling. Now, group 1 and 2, that follows the filling and removal are the same. We simply remove the ns electrons, the last ones in with the first ones out. The main group metals, that is groups 13 through 16, at the bottom, those are the metals, the main group metals. You remove the NP electrons, but then you remove the NS. You don't remove the N-1Ds. So you remove the NS. So this is a case where removal differed from filling. For the transition metals, you remove the NS before you remove the N-1D, so that differs. And then the nonmetals, they add a p electron, so that's similar to our filling rules. So you should go through and make sure you understand these, because this will be important as we think about forming ions and forming chemical compounds. Next, we're going to look at magnetism. We're not going to think about the magnetism that you're normally, experiencing, which is something called ferromagnetism. There's just a few elements that are what we call ferromagnetic. That is, they form very strong magnets, and they're formed when you take a group of atoms together and they form collective electron motions to create a strong magnetic interaction. We're going to look at a weaker type of magnetism called paramagnetism. And then we're going to look at its companion, that is the absence of attraction to a magnetic field, that is diamagnetism. So a species that has one or more unpaired electrons is paramagnetic. It exhibits paramagnetism. It is attracted by a magnetic field. Here we have silver metal. So if I have an individual silver atom, this is its electron configuration. 5s1, 4d10. Has a filled d subshell. And it turns out to be paramagnetic. It's attracted into a magnetic field. A species with all its electrons paired is what we call diamagnetic. It exhibits diamagnetism. It is not attracted, and in fact, it is slightly repelled due to the permeability of free space by a magnetic field. So if you take and look at, here's a figure that shows how if we take either a diamagnetic or paramagnetic material and put it into a magnetic balance, what's called a GUI balance, you'll see these two different responses. So in the upper figure, you have a balance, and on the green side, you have a box that balances the scales for mass, and then the little blue weight that's attached has the same mass as the green box, and that's the blue weight there is a diamagnetic sample. And if you bring an electromagnet nearby, you'll see that it's slightly repelled upward. Below that, we see in kind of rust color is the paramagnetic material. And that's attracted to the magnetic field. So it'll be pulled down. And in fact, depending on what the force is on pulling, that tells you how many unpaired electrons you have in your sample. So this magnetic properties can tell us something about the electron configuration of an ion. Now let's take an atom of titanium. So titanium is a transition metal. It's the second lightest transition metal in the periodic table. So in row 4, as you go across, you have titanium right next to scandium. So it's in the 4th group, group 4. So titanium has 4 valence electrons. Its electron configuration would be 4s2 3d2. And in fact, it shows to have 2 unpaired electrons in the atom. If we form a doubly ionized form of titanium in solution, so a titanium 2 plus ion, you might think, well, maybe that still has a, maybe that doesn't have a magnetism, because the last electrons to go in were the 3d electrons. But in fact, titanium 2 plus is magnetic, as the 4s electrons that are removed first. Titanium 2 plus has 2 unpaired electrons. It's paramagnetic, and that proves to us that the 4s electrons are lost before the 3d electrons. So this is how we understand, or how we learn what the electron configurations for these elements look like in some piece. So the last step we're going to look at, the last piece we'll look at, is ionic size, and compare this with atomic size. We can take, for example, sodium as an atom. We know that's a big atom. Sodium is in the alkali metals. It's in group 1. Those are the biggest of our atoms. But if we pull off one electron and form sodium ion, what happens? Well, that turns out to be a much smaller species. And in general, cations are smaller than their parent atoms from which they come, while the anions of those atoms are larger. The ionic radius increases down a group as n increases, which we expect. Cation size decreases as the charge goes up. So the +1 ion is the biggest, the +2 is the next biggest, the +3 would be the smallest of the group. An isoelectronic series is a series of ions that have the same electron configuration, the same number of electrons, but within that series the ion size will decrease with the increasing nuclear charge. So if you have if you have a series of 6 atoms that all have the exact same number of electrons, but one has a 3- charge, that'll be the biggest. 2- will be next, the 1- will be the next after that. Now you can't form gaseous ions of a 3- ion, but you can form, for example, nitride and 3- in a solid. And then the 1+ is the next biggest, or smallest, then 2+, and then the 3+ would be the smallest of these ions. Ionic radius is determined very similarly as to metallic radius, but typically we will use multiple salts for something to determine the ionic radius of a particular atom. And here we see a comparison of ionic radius versus the corresponding atomic radius. So on the left-hand side, we see for metals, the purple is the atomic radius, and then the little gray is the ionic radius. And you can see the ionic radii for the metals are smaller than the atoms because those are all cations. And on the right-hand side, the red represents the atom, and then the gray represents the ion, but in this case, it's the anion, and we see that they are larger.